Hello everyone and welcome to this tutorial in machine learning for core engineering disciplines and NPTEL course. In the last video we had started out with a tutorial on simple linear regression, and we were trying to use a data set based on the formation times and probabilities of nanopores in two-dimensional materials. And it was quite instructive to look at what are the kinds of Python commands that can be used and how we can do test train split, how we can look at the R square and the MAE of the model, and how we can make a parity plot for not only the training set but also the test set to understand how well the model is performing. In today's video we will take a step forward and we will try to look at things like ridge regression and LASSO as well as hyperparameter tuning, and we will see how these kind of things can be done. So let us go ahead and get started. So last time, just as a quick refresher, you had looked at linear regression using Python, and first we had imported all the data into the Jupyter notebook through the use of the pandas package to read our CSV or Excel file. And as a reminder, the data is taken from this particular paper here, but you are free to use any particular data set that is of particular interest to you, right. And this was again, the data set consisted of 22 different features and 2 target variables and about 21,000 data points. Right, we are basically trying to featureize nanopores in two-dimensional materials. Now this is where your expertise as a core engineer is going to come in, whether you are a chemical, materials, mechanical, aerospace, civil, electrical, or biochemical engineer, right. You need to come up with the sort of physical features that can represent your system properly, and then you have to try to see whether those features are enough to train the kind of machine learning model that you want. In this case we looked at the types of atoms at the edges, so these are called zigzag atoms, armchair, corner, and singly bonded atoms, and then we use these kind of metrics as features for our ML model. Okay, so yeah, all these things are again a refresher from the previous class. You can make a plot to understand how the data is distributed, and like you can see, it's a skewed distribution, particularly for nanopore probabilities. It's very highly skewed. I'm only showing the histogram for the formation time, but you can plot on your computer the histogram for the probabilities, right. You can also look at scatter plots and so on and so forth. And in the last class we discussed the use of this linear model from the scikit-learn library to implement a linear regression model, and we were able to look at the R squared score as well as the coefficients in the model, right. And this was the way to get the metrics like the mean absolute error through the sklearn metrics module, and we are also able to get the root mean squared error. We use the np.square root function to take the square root of the mean squared error here. And finally we discussed things like the test train split, right. Obviously we have to leave out some data for testing the ML model. So here we have left out 25% of the data for test size and 75% of the data is used to train the ML model. This 75-25 split is fairly common. However, depending on the size of your data set, if the data set is too small, then you may not have the luxury of using 25% for testing the model. You may only be able to use say 10 or 15% of the model to test the data set. So it all depends on the size of the data set that you have, but this 75-25 split roughly works quite well. Okay, and here we are looking at the unseen data performance, right, unseen model performance on the data, and this is again done through the sklearn module, scikit-learn module. And finally we saw the code that can be used to make these parity plots. We are using the scatter function from matplotlib.pyplot, and we are predicting the true values, right, on the x axis and the predicted value on the y axis. That is how a parity plot works. And for the training data we are using blue color, and for the test data we are using green color to show the data. This alpha just means the transparency, that we do not want the points to be solid and opaque, so that we can view these overlapping sets of data. And like I said, you can predict the train MAE r square and the test MAE r square, and these can be printed here. The other interesting thing was that there was no overfitting really for the prediction of the formation time. However, the ML model, the linear regression model, failed miserably when it came to low formation times, and this I used to explain that in the paper, right, that I had referred to. We actually developed a two-stage ML model, first to classify whether it is a low formation time or a high formation time nanopore, and if it is a high formation time nanopore, we made use of this light GBM, light gradient boosting machine decision tree based model, whereas here in the low data regime we used a simpler model. So these kind of things can be done, right. Once you know how the model performs, you can tweak it to get the best performance out of it, right. And yeah, these are the parity plots from the paper that I had referred to in the Journal of Chemical Physics, and you can see that these parity plots look quite good. So the other thing we had discussed is we can obtain physical insight into the ML model, right, and physical insight means you get a feel for which features are contributing in what ways to the ML model. Some features may have a positive impact on the target variable, some features may have a negative impact, and these are the kinds of things that is very readily visible in a linear regression model. The more the complexity of the model, the more the physics gets obscured or obfuscated, and this is a trade off that as engineers we have to make. Really complex ML model may perform really well, but then you won't know why you are getting the predictions that you are seeing. However, simpler ML models, although they may not work as well, they do provide a lot of insight in terms of the relationships between the features and the target variable. Alright, and this is where we had ended the last tutorial. We saw that the parity plot for predicting the probability of formation of a nanopore, that was actually terrible using linear regression, and that is partly because some of the probabilities are really low. They are like 1 in 10,000 and others are more like maybe 15 times in 100, and this made the use of the Tweedy loss function particularly important for predicting the nanopore probabilities through an ML model, and that is something you will figure out if you read that paper. So in today's tutorial we are going to move forward and we are going to look at ridge regression, and the motivation here is that perhaps we can improve the performance of this model by trying out ridge regression, right. So that is the whole motivation, and ridge regression is also available in the sklearn model, the scikit-learn model, and yeah, you can fit, right, using the train data a ridge regression model. However, what you see here is that I am still working with the formation time as the target variable here. As you saw on the last page, predicting the probability, right, with such simple models is very complex. So you do need a two-stage ML model. So we are not going to talk about that in this tutorial. We will stick to the earlier target variable of formation time, right. So here we are applying this ridge regression here, and we are looking at things like the train MAE, the train R square, the test MAE and the test R square, right. So these are the values here, and these are sort of comparable, right, to the previous model, and you can see even the parity plots look quite similar. Okay. In this case, right, you know that there is a regularization parameter that can be used, and this is the weight given to the sum of squares of the coefficients, right, in the in the loss function, right. The sum of squares of coefficients has a negative penalty because you do not want any particular feature to assume too much importance, and you can see the alpha parameter here. right. So, this alpha here, that is the weight given to the sum of squares, right, of the coefficients in the loss function. If you remember the loss function, it is the sum of the usual mean squared error plus a regularization term, and that regularization term, the higher the alpha, the more penalty there will be if the coefficients are really high. Alright, so I hope that makes sense. So, we are going to use that and see how things work. So, one thing to note is that the model can be improved by developing a two-stage procedure, wherein a classification model is first used to find whether the formation time is low or not, and then a separate regression model is used for each class. This is something I have mentioned earlier. This is also something that you can try on your own. Alright, so on to the performance metrics, right. This is what you get when you train the ridge regression model with a regularization coefficient of 1, right, and this is now for the probabilities, right, the true and the predicted probabilities, and the results are given here, right. So, again the results are quite abysmal, right. The model is performing really poor on the probabilities, although on the formation time the model is reasonable, though still the parity plot is not nice in the low formation time regime, though in the high formation time regime it does work reasonably well. On the other hand, for the probabilities the model really fails even when you use ridge regression. Okay, so that is the discussion on ridge regression that we had. It is a short discussion. Now, I want to move ahead and talk to you about unraveling correlations in the data set using a module known as Seaborn. This is another Python module, and the functions in this module, they allow you to conveniently visualize the relationships that exist between various variables, and it allows for data visualization and plotting also through matplotlib, right. So, first you need to install Seaborn. The command to do that is again very straightforward. It is just pip install Seaborn, and then once you have the Seaborn package, you can very easily create a scatter plot of y versus x for each variable in the data set, right. So, our data set had 22 features and 2 target variables, and you can create a y versus x plot for each of these, right, and it can be arranged in a grid, and that is done to the following command. You import Seaborn as Sn, that is the name I have given here, and then using this pair grid function, using the X matrix, you can just get the the scatter plots, and then you can plot them here using this command, right. So, this is basically the first row corresponds to the first feature, and the first column also corresponds to the first feature, right. So, when you plot the first feature versus the first feature, obviously you will get a straight line, right, that is y equal to x. So, that is what you see here, and that is always what happens with the diagonal. So, if you plot the second features versus the second feature, third feature versus the third, fourth versus the fourth, and so on and so forth. So, on the diagonal you will always see a straight line. So, that is not where things are interesting. Things are more interesting if you look at these other plots here, where some very nice sort of patterns emerge, right. So, you can see whether two variables are negatively or positively correlated. For example, here the first variable here, and this is 1, 2, 3, 4, 5, 6, right, the sixth feature, right. The first and the sixth feature, they are positively correlated, the first and the seventh as well. So, these are the kinds of things you can see. These two sets of features in this row and this column, they are negatively correlated. So, these kind of insights, it would have been very difficult to sort of immediately gather, but once you have these kind of parity plot, these kind of scatter plots, it is very easy to see how the variables are distributed. Okay. So, now it is also possible to determine the correlation coefficients between each pair of variables in the data set, and this will allow you to create a heat map using Seaborn. So, that is also very nice, because a heat map allows visualization through the use of colors, right. So, first we actually compute, right, the correlation matrix, and then the correlation matrix can be visualized as a heat map, right. So I'm feeding the correlation matrix here, so you can see that these are the correlations between various variables. Of course, again on the diagonal here every feature is correlated with respect to itself, so you can see that the number on the diagonal is always 1, but you can also see other things like this feature, right, the first and second, third, fourth, fifth, sixth, seventh, right, 1 2 3 4 5 6 7, these are also correlated with each other, right. So there are some variables that are correlated with each other. In principle, if you want, they can be removed before you make the ML model. However, if you're using regularization, then it's okay, because the model will learn to figure out whether to weight both of them equally or none of them at all. But this is a really nice way to just right get an understanding of the correlations that exist between the various variables, and to weed out the features that you do not want if they are very highly correlated, right. So yeah, you can use this heat map as it is called to figure out which variables have the highest correlation coefficients and which have the lowest, and it may lead you to figure out some unexpected correlations, right, yeah, which otherwise you may not have known, right, or may not have expected. That is the advantage of visualizing the data, right, without pre-assuming anything about what is happening. Okay. So now we come to the part wherein we discuss about cross validation, right, for linear regression and lasso. As you know, cross validation has several benefits, right, or several use cases. One is to get an estimate of the generalizability of the ML model. You want to see how small variations in the training set and the validation set, they change the performance of the model. So you can get an average value of the model performance over various validation sets. The other advantage is that hyperparameter tuning, right, can be done as part of the cross validation procedure, because hyperparameters are model configuration variables or training configuration variables, and these need to be set before the training can begin, and the only way to really determine the optimal hyperparameters is to do cross validation, right. So that gives a good estimate for the kinds of parameters like regularization parameters in simple linear regression and lasso, but of course more complex hyperparameters, for example neural networks, you can have the number of layers, the number of nodes in every layer, the learning rate, the activation function, and so on and so forth. Now for this particular part of the tutorial, wherein we are looking at cross validation of linear regression and lasso models, we are using, right, ML model that predicts the hydrogen adsorption free energy on a particular catalyst surface and nickel phosphide Ni2P, and this is doped by various non-metal dopants. And why we are interested in this delta H delta G of hydrogen adsorption, the Gibbs free energy of hydrogen adsorption, is because this value is a good descriptor for the catalytic activity of any material for the hydrogen evolution reaction. You know, this reaction is very important in electrochemical water splitting. As you know, water splitting is one of the ways to produce green hydrogen. Typically the hydrogen that we use, it producing that involves emitting a lot of carbon dioxide, and carbon dioxide of course causes global warming, that is very well known. So people are looking at alternative ways to produce hydrogen without emitting CO2, and this water splitting is one way of doing it. And when you split water, you evolve hydrogen and you evolve oxygen. So one of the reactions involved is hydrogen evolution, and in this part of the tutorial we want to develop an ML framework which can predict, right, how well a catalyst will perform, right, for water splitting, right. So just reiterating what I just said, water splitting is a CO2 free route to produce hydrogen for use in various industries. Yeah, it's used in the petroleum industry, ammonia production, methanol synthesis, and most of the hydrogen right now is produced from steam methane reforming, which releases significant amount of CO2 into the Earth's atmosphere and causing issues with global warming. So therefore, researchers are searching for new catalyst materials which can catalyze this particular reaction efficiently, and we desire a moderate value of this delta G that is neither too high, which is indicative of difficult desorption, or nor too low, right. So that is the sweet spot that we are targeting. So we want to develop an ML model that can predict this value as a function of the dopant added to the surface, right. So this type of a problem is very important from the perspective of the core engineering disciplines. Although we are talking about materials design or catalyst design here, I am sure you can think of some good examples in your specific discipline or domain which will require you to predict the performance of a material or the performance of a device or a process, right, that you would like to optimize. Okay. So the data set under consideration has been obtained using what is called quantum mechanical density functional theory calculations, and it is derived from this particular paper published in the Journal of the American Chemical Society in 2018. And how you can obtain this data is you can open this paper on your computer in your browser and then download the supporting information of this article from the journal website, and that gives you a zip file wherein there is a CSV file called processdata.csv, and this file contains 28 features corresponding to 56 different doped systems of varying composition, right. So it's a small data set, right. This is also one of the challenges of carrying out machine learning in core engineering disciplines. Typically, if you talk about things like computer vision, natural language processing, in computer vision you are trying to figure out things from an image. In natural language processing you are handling text, right. So in both of these cases there is ample and plenty of data, right, terabytes of data available on the internet. However, when it comes to problems in the core engineering disciplines, the limited availability of high quality data is really a challenge, and this is where we have to innovate in developing models that are simple and yet can get the job done. That is where our expertise as an engineer or a scientist will come into the picture. Okay. So with that background in mind, right, these are the features available in the data set. The authors use these features, and I have provided a description of each of these features and the symbol that is used. This could include things like the number of dopants in the surface layer, the distance between various atoms, the angular information, right, the geometry of the surface is important. So that also includes things like distances and so on and so forth. Okay. So with this brief understanding of the data set, and you are free to pause here and understand each of these features, but I am going to go ahead in the interest of time. So what you can do is, using our previous Python and scikit-learn experience, we can first train a linear regression model again with a 75-25 split for the training and test sets, and we again do the standard procedure. You import pandas, you read the Excel file, then you can drop, right, the features, right, or any unwanted columns, right. So that is your data matrix X, where the rows are the each point and the columns are the features, and you can also initialize the data, right, delta G of adsorption of H, that is the quantity we want to predict. Okay. So you have the X and Y matrices, and then yeah, you can train a simple linear model. Again I am doing test train split here with a 75-25 split. Again I told you this random state is very important because that determines how the splitting is happening, and if you change the random state you will get a different test train split. If you did cross validation, or if your data set is huge, usually it should not matter what the random state is, but for very small data sets like the kind we encounter in core engineering disciplines, it could be a problem, by the way, right. It may happen that you need a, if you change the random state, then you start getting slightly different answers or even significantly different answers. These kinds of things can happen in small data sets, and it is best to be honest and report exactly the results that you are getting, right, and acknowledging any limitations of your model. So here I am printing things like the test RMSE, but we do have the R square as well for both the test and the trained data, right. And we also made a parity plot here. These are again standard commands using matplotlib, and by now you must be familiar with it. You can take the time to enter each of these commands into your computer, into the Jupyter notebook, and then let them run, right. So this will obviously take some time, and I encourage you to pause the video at this time to do that, right, so that you become more and more familiar with the coding in Python and to implement these kind of simple ML models. So assuming that you have done all this at your end, you have put in the hard work, these are the results that you would probably get. It is actually not bad, right. The parity plot at least looks nice, but what is concerning here is basically the train R square is just 0.95, whereas is 0.95, which is very nice, but the test R square is only 0.57. So that is clearly a cause of concern, right. It is problematic, and this is also reflected in the train MAE being much lower, right, almost 1/3 of the test MAE. So you can clearly see that there is some problem with this particular the way the model has been made. It is clearly a case of overfitting. So your model is doing well on the trained data, but it is not doing well on the test data. So I hope this is a practical example of overfitting that you can take back from this lecture. Okay. So what is the take home message? The take home message is that the R square score on the test set is not as good as one would expect in a high quality ML model. The MA is still reasonable. So now comes the role of cross validation, right. We discussed that it does have a role in preventing overfitting, right, because you change the train and the test set, and then you decide what really the model performance is. So one can check if the model is robust across various choices of the training set by using, in this case I am using 5-fold cross validation, and this is accomplished using the k-fold and the cross val score modules in the sklearn model selection module, right. So from sklearn dot linear model I am importing linear regression, from sklearn dot model selection I am importing cross validation score and k-fold. This is again simple train test split, that is the random state. So I am defining the linear regression model, defining the 5-fold cross validation procedure, that is the number of splits, whether you want to shuffle, what random state you want to use, and finally you can get the cross validation score of this linear regression model, right. So first you have to define the model, and then that model goes in here as the argument, and the type of cross validation is given here, that is the k-fold cross validation, and you have to give the metric that will be used as the cross validation score. In this case I am using the negative mean squared error. So why am I adding a negative sign to the mean squared error? That is because typically a score, right, a higher score is better, right, but when you are training an ML model, the loss function is as low as possible, right, it is as low as possible. So therefore I am taking the negative of the mean squared error, because if the mean squared error will be very low, right, then the score will be high, the negative. And finally if you want to still display the MSE scores, you can take the minus sign and multiply that with scores, and finally you can iterate over all the folds and you can print the MSE score for each fold, and you can also print the average MSE. So this is what it looks like: fold 1, fold 2, fold 4, fold 5, nothing out of the ordinary, but look at fold 3, the mean squared error is huge, right. So, the mean squared error in 4 of the 5 folds is very low, but something strange is happening in one of the folds, and this may occur even if you change the random state, right. This implies that the model is being overfit and one needs to adopt a regularization strategy to overcome the problem, right. So, that is where we come to implementing the LASSO method and to optimize the regularization parameter. You already know that LASSO stands for least absolute shrinkage and selection operator, and one needs to choose this regularization parameter that weights the linear regression, the sum of the absolute values of the linear regression coefficients. So, how do we decide what value of alpha to choose? So, this can be done using 5-fold cross validation as is shown below, right. So, again I am importing, right, this linear model LASSO from sklearn.linear model. I am also importing here, apart from k-fold, something called grid search CV, and this we saw a few lectures ago, that grid search CV is a way to systematically scour through parameter grids, right, for hyperparameters and then figure out which is the best one. The good thing here, the grid only has to be made for one particular hyperparameter, that is alpha. Now, if you had much more complex ML models, you will have to vary the other hyperparameters as well, not just the alpha regularization parameter, and that is something we will come to in the future lectures as well as tutorials, right. So, here we are implementing LASSO, number of splits is 5 or number of folds is 5, you do specify the random state, and here is how we do grid search CV on this particular model, the LASSO regression. Yeah, this is the CV score, the negative root mean squared error, and so on and so forth. And finally, you can print the results, right. So, this is nice because you also get the best out of the grid you have chosen. So, the alpha values I have given are 0, 0.1, 10, 100 and 1000, those are the possible values that you can use, and you can clearly see here that the best performance is obtained using alpha is 0.1. So, if you use alpha is 0, the score is 10, with alpha 0.1 it's 0.16, with alpha 10 it's 0.23, 0.24 and so on. So, basically there is an optimal value of alpha. Beyond this, right, what is happening is the regularization is so much that the model is not able to learn effectively. So, there is always a trade off as to how high you want this regularization parameter. So, we see that a value of alpha 0.1 is predicted to be the best, leading to a cross validated RMSE of 0.167, that is really nice, and alpha equals 0, which is normal linear regression, leads to a large value for the average RMSE due to overfitting. Therefore, we have successfully demonstrated the use of regularization to ensure better generalizability of the ML model using the LASSO method. Not only that, we have demonstrated the use of grid search cross validation and 5-fold cross validation to tune the hyperparameters of the ML model. So, I encourage you to code something like this at your end for your problem of choice, and you can work with LASSO, but also with more complex ML models that we are going to be covering in the upcoming lectures and tutorials. So, this brings me to the end of this particular video. I hope you enjoyed learning how to implement things like LASSO, ridge regression, how to find the regularization parameter using 5-fold cross validation and grid search CV, and hopefully you will implement some of these for your own interesting problems in engineering and science. Thank you for joining today, and I look forward to seeing you next time.